All right, so section 3.3 is when things start really getting fun. If you could possibly believe that calculus could be fun, which I certainly think it can be. We start learning a lot of the shortcut rules for finding derivatives, so we don't have to use that big long difference quotient with the limit every single time. There's a lot of patterns in how these derivatives work. And there's a lot of really quick, easy ways on how to find the derivatives without having to do all of that crazy algebra. So 3.3 is where we start introducing some of these quicker, easier rules for differentiation. The key in all of this is to remember that derivative equals tangent slope. So that's going to help us out a lot with the first couple of derivative rules that we're going to see. So our first rule is the constant rule. And at the end of this section, we'll make one big list again of all of our rules together, but we're going to go through them here one at a time with a couple of examples of each. So this section is really, really important for chapter 3, and it's really important for the understanding of the rest of the semester, so this video is going to be a little bit long. So our constant rule, this tells us how to take the derivatives of constants, and a constant is just a number. So if we want the derivative for any constant, so remember, derivative is tangent slope. So technically, what this is saying, I'm not going to tell you the answer yet. This is saying we have y equals a constant, and we want to know what its tangent slope is. So if y is a constant, that is a horizontal line. What is the slope of a horizontal line? It's 0. So no matter where that horizontal line is, we can move it up and down the plane. If it's a constant, it's just going to be horizontal always, and its slope is always going to be 0. So anytime you take the derivative of a constant, it's going to equal 0. For example, the derivative of 5 is 0. The derivative of negative 3/8 is 0. The derivative of pi, it's an ugly constant, but it's a constant. It's 0. The derivative of any constant is equal to 0. Okay, nice and easy. Start out easy. The derivative of a constant is equal to 0. The next rule I'm going to go over is not really a rule that's written in our book, but it leads up to the next rule, which is the power rule. And this is the rule for linear equations. I'm going to call this the linear rule. So if we want the derivative for, and let me actually write this as mx plus b, because that's typically how we write the equation for a line, mx plus b. So what we're really saying here, if you think back to what we know so far about derivatives, derivative equals tangent slope. What we're saying is we have the graph y equals mx plus b, and we want to know what the tangent slope is. So this graph is a straight line. I don't know what the slope is. It's in the equation. I'm just making up what this thing looks like. But because it's a straight line, If you were to try and draw a tangent slope, it would be right on top of your line, and it would be the same everywhere. The tangent slope would always equal m. It would be whatever the slope of the line is. That the plus b, the intercept, isn't going to make any difference on the slope. This is always going to be equal to m. The derivative for any linear equation is just the slope of that line, because a line has a constant slope. So a couple of quick examples. The derivative for negative 2x plus 5. Remember, derivative means slope or tangent slope. So the slope of that line is negative 2. The derivative of 1/3 x minus 7/3. It doesn't matter that there's fractions in there. That's not going to make any bit of difference. That is a line. The way that I know this is a linear equation is because x is to the power of 1. So the slope of this line is 1/3. The derivative of 12 minus x. So I rearranged my terms a little bit there, so you need to be careful. So the slope always appears as the number in front of your x. It's the coefficient in front of the x, and that coefficient includes the sign in front of the x. So if we look at what we have here, in front of the x, all we have is a subtraction symbol, and there's no number, which means we have a little imaginary 1 there. So the slope of this line is going to be negative 1. The 12 is a constant. That's our y-intercept. That's not going to have any effect on the slope. The slope comes from the coefficient on your x when you're looking at lines. So the derivative for constants are always 0. And the derivative for linear equations, well, linear equations have a set slope along the entire line. So the derivative is just the slope. One of the most important rules that you're going to use over and over and over again for all of the calculus classes that you're going to take from here on out is called the power rule. And we're going to use this for lots of different types of functions that look really different, but they all are going to end up having something in common. Anytime we want to take the derivative of something that can be written as x to the nth power, and now there's really not many rules on what n can be. N can be a positive whole number, it can be a negative whole number, it can be a fraction, it can be a decimal. So there really isn't any restrictions on n, except n can't be negative 1. And you'll see why in just a minute when you see what we are going to... is it negative 1? No, it's not negative 1. I'm sorry. That's a different rule. Forget I said that. That's a different rule. So there's no restrictions on n. Anything that we can write as x to the n power, we can do the power rule on. So the power rule says you're going to take the current power and you're going to bring it out front as a coefficient. and then you're going to rewrite your x, and then its new power you're going to get by subtracting 1 from the old power. So the derivative for x to the n is n times x to the n minus 1. So let me show you how this works with an example. And we'll start off with some easy ones, and then I'll show you some much more tricky ones that this also can be used for. If we want the derivative for x cubed. So here it's x to a power, and the power is 3. So the rule says take that old power and bring it out front as a coefficient. And the new power we get by subtracting 1. So 3 minus 1 is 2. So remember, the derivative tells us tangent slopes. This is a formula for finding tangent slope anywhere on this graph. If I want to find the tangent slope anywhere on the x cubed graph, I would plug the x coordinate into 3x squared. And it would tell me what my tangent slope is there. The derivative for x to the 7th. It's x to a power. So the rule says bring the power out front as a coefficient, and then subtract 1 to get the new power. So 7x to the 6th. Now we can do our limit definition that we learned in section 1, and we would get the same answer. But as these powers get larger and larger and larger, the algebra is going to take longer and longer and longer to calculate and simplify. Because remember, our first step is to calculate f of x plus h. So if I had to do x plus h to the 7th, that means I would have to write out x plus h 7 times and FOIL all of those out to get them simplified. And that would take a very long time. So these two are pretty straightforward. They're x to a power. Some other ones that are not quite as straightforward is roots. We can also do roots with our power rule because a root can be written as a power. Roots are fractional powers. So our first step is to rewrite this so it's written as x to a power. So a square root is a 1/2 power. Once we see it as x to a power, then we do it just like we did the other ones. The old power comes out front as a coefficient, and then we subtract 1 to get the new power. A 1/2 minus 1 is a -1/2. Now, most of the time, we're going to want to write our answer as simple as possible. So a -1/2 power, negative means it wants to be moved to the denominator. And then we just said 1/2 power means square root. So technically, x to the -1/2 means we have a square root in the denominator. And I believe we did this exact problem back in section 1 and got the exact same answer, except we had to do it the algebra way, and we had to do we had to multiply by the conjugate to rationalize and go through all those algebra steps, and it took a lot longer to get that same answer. So this works for every type of root. We could also do a cubed root. The first thing we would want to do is rewrite it as a power. So a cubed root would be a 1/3 power. So I haven't done the derivative yet. All I've done is rewrite my cubed root as a 1/3 power. We need to see it written as x to a power so that we can do the power rule on it. So the power rule says bring your old exponent out front as a coefficient, and then we're going to subtract 1 to get the new power. So 1/3 minus 1 is -2/3. And if we rewrite this, our fraction has a numerator value and a denominator value. And when that happens, the denominator value always indicates a root. The numerator value stays as an exponent. Okay, so that 2 is going to stay as an exponent, and it's going to stay as x squared. But the denominator means we still have a cubed root going on here. And then the fact that it turned negative means it wants to be moved to the bottom. So we've got 1/3 cubed root of x squared is what it simplifies to. So it moved to the bottom because of the negative. It's a cubed root because of that 3 in the denominator of our exponent. And the numerator of our exponent just stays an exponent. So we can use our power rule for roots. Another thing we can use our power rule for are rational functions, as long as they're fairly simple. So if we have like 1/x cubed, I can use the power rule on that, but just like the roots, I need to rewrite it first. We've got to see it as x to a power, not as a fraction, not in the denominator, just x to a power. So I need to bring this expression up to my numerator. I need to use algebra to rewrite it first. So I can bring my x cubed up to the numerator if I rewrite it as x to the -3. That's the same thing as having x cubed in the bottom. Once we have it written as x to a power, no longer in the denominator, no longer a fraction, then we can do the power rule on it. The power rule says bring your old exponent out front and then subtract 1 to get your new exponent. So -3 minus 1 is -4. And if we want to rewrite this simplified, this piece has a negative power, so it's going to move to the bottom. Now be careful, because -3, your coefficient in the front, that does not have a negative power, so it is not going to move to the bottom. That's going to stay in your numerator. Only the x has a negative power, so we can move it to the bottom and change it back to a positive power. And one more real quick, and we'll look at just a couple more rules. The derivative for 1 over the 8th root of x. The derivative for 1 over the 8th root of x. We can rewrite this as just x to a power. But there's a couple things we need to do. First of all, we need to get it up out of the denominator. And we do that by using a negative exponent. Second of all, we need to write the root as a power. And we do that with fractional exponents. So this is the same thing as x to the -1/8. Once we have it written as x to the -1/8, we can use the power rule. The power rule says to take the derivative, we move that power out front as a coefficient, and then we're going to subtract 1 to get the new power. So -1/8 minus 1. If you can't do that in your head, type it in your calculator. Most likely your calculator is going to give you some weird decimal. So under the math button, the first option says change it back to a fraction. So in your calculator, if you type in -1/8 minus 1, it's probably going to say -1.125. Go to math option 1 and tell it to change it back to a fraction, and it will say -9/8. So remember what we did with the last one that had a negative fractional exponent that had a value in the numerator and denominator. The denominator means we're still working with a root. The negative means it wants to go to the bottom. The numerator stays as an exponent. So this is -1/8. That's our -1/8. And then the x is going to be inside of an 8th root, and it has a 9th power. That is our derivative. That is the formula we would use to find tangent slopes on the graph of this function. Much easier and faster than going through that whole limit definition. Our next rule is not really its own rule of how to do new derivatives. It's called the constant multiple rule. And it tells us how to deal with coefficients. So the constant multiple rule says if you're taking the derivative of some function that has a coefficient in front of it, that coefficient is not going to affect how you take your derivative. This derivative says, technically, take the derivative of the x's. It's the x's that we apply our derivative rules to, and the x's are inside of this function. Now, c is still going to be part of the answer, but it's not going to affect how we take the derivative. So technically, we can just ignore the c and we can pull it out and just worry about taking the derivative of the function. The c is a coefficient, and it just gets carried along to the answer. So this would be c. Now remember what the notation is for the derivative of f of x? It's f prime of x. So we just do whatever our rule is for finding the derivative of f, and the c is just still a coefficient. You don't do anything special with coefficients besides carry them along to the next step in your answer. So if I wanted to do the derivative of -4x to the 7th. So x to the 7th, I would do the power rule on. What's different here is that there's a -4 in front, which is a coefficient. So really, I don't have to do anything with the -4 except carry it to my answer. Just carry it along to your answer. What I need to do is apply my power rule to my x to the 7th. And the power rule says bring your old power out front and subtract 1 to get your new power. So 7 minus 1 is 6. And we can simplify that a little bit because I've got two numbers being multiplied together there. -4 times 7 is -28. So our derivative is -28 x to the 6th. So the -4 coefficient, it just transfers onto the answer. We only apply our derivative rules to x's. the derivative for 16 times the square root of x. We're going to want to rewrite it because we need to see square root of x as x to a power. So this is the same as 16x to the 1/2. Now the 16 is just a coefficient, so we just transfer it over to our answer, and we only need to apply our derivative rules to the x to the 1/2. Since it's x to a power, we do the power rule, which says bring the old power out front and subtract 1 to get the new power. So a 1/2 minus 1 is a -1/2. And there's two things we can do here to simplify that. We can multiply the 16 times the 1/2. That will simplify to be 8. And then we can move x to the -1/2. Negative means it wants to be moved to our denominator. And the 1/2 power means it's under a square root. So 8 over square root x. Okay, so coefficients just get transferred on to the next step. You just bring them along for the ride. Our next rule is called the sum and difference rule. And this is going to allow us to take derivatives of functions that have multiple terms in them. The sum and difference rule says the derivative for f of x plus or minus g of x, if you've got multiple terms being added or subtracted, all you do is take the derivative of each piece or each term individually. So we're going to take the derivative for the f of x and then add or subtract that to the derivative of g of x. This only works for addition and subtraction. It does not work for multiplication and division. Just addition and subtraction. It's called the sum or difference rule. So the notation for the derivative of f of x, that's f prime. And if we follow those same conventions for g, the derivative for g of x would be g prime. So anytime we've got terms separated with addition or subtraction, we just apply the derivative rules on each of the terms individually. So we can take derivatives of big long polynomials by just applying our derivative rule on each individual term. So one crazy one here, let's take the derivative of 5x to the 4th minus 9x squared plus 12 cubed root of x minus 20. Might look difficult. It's really not. It's not any more difficult than any of the other ones we've been doing. So this expression has 4 different terms. There's 1, 2, 3, 4. I'm going to take all their derivatives one at a time. Take all their derivatives individually. And then just keep the same operations in between. So first we have to take the derivative of 5x to the 4th. Now the 5 is a coefficient. It's just going to carry on to the answer. The derivative for x to the 4th, we do the power rule. Old power comes out front, and we subtract 1 for the new power. And I'll do another step to simplify this stuff. And then I keep my operation of minus, and I can go on to the derivative of the next piece. 9 is a coefficient. It just carries down to the answer. And I do my derivative for x squared. So that's x to a power. The power rule says bring the old power out front and subtract 1 for the new power. For my cubed root, we're going to want to rewrite that as x to the 1/3. The 12 is a coefficient. You want to keep your plus. So the 12 is just going to transfer down. Now the cubed root, which is x to the 3rd, that's just x to a power. So bring the old power out front and then subtract 1 for the new power. My last term is a constant. It does not have any x's in it. So remember, the constant rule was the very first one we talked about. The derivative of a constant is 0. If you want to, you can say minus 0 in case you ever look back at this and you want to know what happened to it, but the derivative of a constant is 0. Now I'm going to clean this up a little bit for our final answer because we have some coefficients that can be multiplied together. We've got a negative power that we should move to the bottom. So my first piece, I've got 5 times 4. That's 20x cubes. Then I've got subtraction. I've got 9 times 2, that's 18. And we usually do not write powers of 1. So really this is just 18x. And then we've got addition. 12 times 1/3, that is equal to 4. And let me actually write that up higher because this last piece is going to be a fraction because x is to a negative power. That means it wants to be moved to the denominator. So 4 over, and the denominator is a root. So it's a cubed root. The numerator stays a power, cubed root of x squared. And the negative means the whole thing wants to go to the bottom. And then minus 0 we don't need to write. Subtracting 0 doesn't affect the value. So we had more derivatives to do. It's like doing 4 derivative problems because there's 4 terms in there. So anytime you've got addition or subtraction in your function, you just do each of the derivatives individually and keep the same operations in between. So minus stayed minus, plus stayed plus, minus stayed minus. And then we just clean it up in the end. Our last brand new rule for this section is the derivative for the exponential function, which is different than the power rule. It looks kind of similar, but it's actually completely different. So you may remember from algebra class, the exponential function is f of x equals e to the x. F of x equals e to the x. And the graph looks like this. On the left-hand side, it's really close to the x-axis. And on the right-hand side, it shoots off to infinity. So there's a special rule we need to remember for the derivative of e to the x. We do not use the power rule on this. Now the power rule is only when the base is x. So if you look back up here at how we wrote the power rule, the base is x and our exponent is a number. We've got the exact opposite going on with the exponential function. Now we have the base is a number because e is the number 2.71828 da 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 da. E is just a number. And our variable is in the exponent. So this is a completely different type of function. It's not a polynomial. The derivative for e to the x This is the easiest derivative you're ever going to do, maybe besides the constant derivative, which is 0. The derivative for e to the x is e to the x. Simple as that. And then we can apply some of the other rules, like the coefficient rule and the sum and difference rule, to spice it up a little bit. But there's not a whole lot we're going to do with it right now. So if I wanted the derivative for 5e to the x plus 3x to the 5th. I've got two different terms here, so I'm going to do their derivatives separately. The derivative for 5e to the x, well, 5 is just a coefficient, so I'm going to carry it on to my answer. And the derivative for e to the x is e to the x. And then I've got addition. Addition just carries on to the answer. 3 is just a coefficient. It's going to carry on to the answer. And then I've got to do the derivative for x to the 5th. So that's x to a power. So we do power rule. Power rule says bring the old exponent out front and then subtract 1 to get the new exponent. And we can clean it up just a tiny because we can multiply the 3 and the 5. So we get 5e to the x plus 15x to the 4th. That would be our derivative. So when we first introduced derivatives, remember we said derivative tells us slope of a tangent line. So we might still be interested in finding slopes. So let's look at a couple of examples where we're specifically asked to find slope or find equation for tangent lines. Anytime you see a problem that talks about slopes or tangent lines, you should automatically think, I've got to do the derivative. The derivative is how I find tangent slopes. We want to find the equation of the tangent line to the graph of f of x equals x cubed minus 5x squared plus 12x at the point 1, 8. We want to find the equation of the tangent line to the graph of f of x equals x cubed minus 5x squared plus 12x at the point 1, 8. So if we take a look at this graph, and this might not be the exact graph, but it's a cubic function, looks something like this. And the point 1, 8 is going to be about here. And the tangent line looks like that. I want to know what the equation of that green line is. So if you think back to algebra class, there are two things that we need to know to write the equation of a line. We need to know the slope of the line, and we need to know a point that the line passes through. They gave us the point already, so that is ready to go. What we don't know is the slope of that line. So as soon as you start thinking, I need to know the slope, we automatically think, now that we're in calculus class, slope is derivative. Derivatives tell us slopes. So we need to do the derivative. We need to find f prime of x. That will tell us the slope for this function, the tangent slopes. So f of x is x cubed minus 5x squared plus 12x. We need to find the derivative. It's got three different terms, so we need to do the derivative of each piece individually. So the derivative for x cubed, if you do the power rule, is 3x squared. Old power comes out front, new power is one less. And then we've got subtraction. The derivative for 5x squared, and I'm going to do this much quicker. If you bring the old power out front, we're going to have a 2 out there with our 5, and it's multiplication, so that's going to be a 10. And the new power is going to be 1, so it's just 10x. The last piece is linear. It's got a power of 1. That's a linear piece. So the derivative is just the coefficient of 12. You can do the power rule on that because you would bring the 1 out front. 12 times 1 is just 12. And the new power is 0. And x to the 0 means there's no x's left. X to the 0 is equal to 1. So the only thing left in that last term is the 12. This formula will tell us the tangent slope anywhere on the graph. But we want tangent slope at 1/8. Well, the derivative is only dependent on the x value. All we have to do is plug in the 1. So we need f prime at 1. So anywhere I have an x, I'm going to plug in a 1. And that will tell me tangent slope at the point 1/8. So I've got 3 times 1 squared, which is 1, minus 10 times 1, which is 10, and plus 12. So we've got 3 minus 10 plus 12. Well, 3 minus 10 is -7. -7 plus 12 is 5. Our line has a slope of 5. So we've got everything we need to set up the equation of a line. We've got a slope of 5, and we know it goes through the point 1/8. So the way that I like to write my lines, we always want our final format to be in slope-intercept form, y equals mx plus b. We know slope is 5, so we can plug that in. And we know we have the point 1/8. Well, I like to use those coordinates for my x and for my y, and then solve for my b. So I'm going to say x is 1, and y is 8. That is one xy coordinate pair that satisfies this equation. So I can plug them in, and I know 3 of those 4 values in that equation. So I can solve for the 4th one. So I'm going to plug in everything that I know. 8 is equal to 5 times 1 plus b. So 8 is equal to 5 plus b, which means b has to be 3. So we know we have a slope of 5 and a y-intercept at 3. The equation for our line is y equals 5x plus 3. Beautiful. So anytime we want the equation for a tangent line, we've got to use the derivative to help us find the slope. And then once we know the slope, they're going to give us a location that we need our tangent line at. So we'll do the slope and we'll use the location, and we can just go back to what we know about algebra to set up our equation. Another thing that we can do with our derivatives here is we can find certain places where specific tangent slopes exist. And this is going to be really helpful in our next chapter. We might be interested in knowing where we have horizontal tangent lines. we're going to identify or find all points on the graph of f of x equals negative 4x squared plus 4x minus 7. Identify all points on the graph of f of x equals negative 4x squared plus 4x minus 7 where there is a horizontal tangent line. If you ever see a problem that says slope or tangent line, those should be big blinking lights in your face to think derivative. This has to do with derivative. I'm going to do something with derivative. And more specifically, it says horizontal tangent line. So I know tangent line means derivative. And what kind of slope does a horizontal line have? We talked about that in the last section. Horizontal lines have a slope of 0. So this question is asking us to find where derivative equals 0. Tangent lines, slopes of tangent lines are found using derivatives, and they are horizontal when they're equal to 0. When those slopes equal 0. So they don't ever come out and explicitly say it, but this is what they're asking us to do. Find where the derivative equals 0. These are going to be very, very important locations in the next chapter. These are called critical values. So we need to find our derivative. We have the original function, f of x equals negative 4x squared plus 4x minus 7. We need to find the derivative and then set it equal to 0 and solve. So this function has 3 different terms. We're going to have to take the derivative of each of them individually. So we're just doing the power rule. If the 2 comes out front, that's going to be a negative 8x to the first power. This piece is linear, so the derivative is just the coefficient. This piece is a constant, so its derivative is 0. So our derivative is negative 8x plus 4. We want to know when this is going to equal 0. So we just have a linear equation to solve. Negative 8x plus 4 equals 0. So I'll subtract the 4 over. Divide the negative 8 over. And we get x equals 1/2. That is not our answer. Be very careful. Always look back at the question. It'll take less than 5 seconds. Look back at the question and make sure you have answered the question that you are being asked. The question says identify all points. Now points have an x coordinate and a y coordinate. All we've found is the x coordinate. So we've got half of the answer. We've got the x coordinate. We need the y coordinate as well. So you need to think a little bit about this. How do we find the y coordinate? I know the x coordinate is going to be 1/2. I know my answer is going to start off as 1/2 comma something. I've got 2 equations here. I've got the original function and I have the derivative. So remember, the derivative gives you slopes. I don't want to put the slope in there as my y coordinate. The original function tells you points on the graph. So we want to plug this back into the original, plug back into f of x to find the y-coordinate, because we were specifically asked to find a point. So we want to find f of 1/2. So we're going to do -4 times 1/2 squared plus 4 times 1/2, and then -7. The original function always tells you points on the graph. The derivative of the function tells you tangent slopes on the graph. So 1/2 squared is 1/4. 4 times 1/2 is 2. -4 times 1/4 is -1. -1 plus 2 is 1, and 1 minus 7 is -6. So when we plug 1/2 into the function, we get back -6. So the point where we have a horizontal tangent line is at an x value of 1/2, a y value of -6. So I warned you this video is going to be a little bit long, and I was not kidding. There is one more thing in this section, and then we will wrap it up, and it is higher order derivatives. What we've been doing is first derivatives. First derivatives are when we apply our derivative rules once. First derivative means apply the rules just once, and that's your answer. Well, we could, if we want to, continue to apply the rules over and over and over again and produce higher order derivatives, like a second derivative or a third derivative or a fourth derivative. And these higher order derivatives do have practical applications for them. So a second derivative means that we're going to apply these rules twice. We're going to do it once and get an answer, and then we're going to do it again. And there's some notation that I need to show you so that we know when we look at it that the rules have been applied twice, or that we're being asked to do it twice. And then so on and so forth. We can do third derivative, fourth derivative, fifth derivative. So back, I believe in section 1, we said one of the applications for derivative is velocity. If the original function is a position function, then the derivative is velocity. Well, a second derivative of that same position function would tell us acceleration. So second derivative has a practical application in the real world. And then third derivative does as well. Third derivative, one of the applications for third derivative is called jerk. And think like when you pull on something really quickly and hard, when you jerk on something. So to take the second derivative of something, there's some notation that we want to use so that somebody knows we did the second derivative, or so that when we see it in directions, we know to take the second derivative. So the ddx are the instructions that tell us to take a derivative. So we might see it twice. So we see it here telling us to do it once, and then once we get that answer, we then do it again. We could consolidate this down and just say d2 dx2 of f of x. d2 dx2. So those 2's mean second derivative. We're going to apply our derivative rules twice. Now you can't jump straight from the original function to the second derivative. You have to do each derivative one at a time in order to progress through your derivatives. So this is if we use the d dx notation. If we use the function notation, we would just add a second apostrophe. That would be our second derivative. For third derivative, we would just have 3's here, and we could do 3 apostrophes. Once we get to fourth derivative, now we could always just put any number we want to up here in the d dx notation, but at some point we have to stop adding parentheses because it gets to be just too much. So third derivative, we can say d3 dx3 or f triple prime. Once we get to fourth derivative, the f notation is going to change because somebody somewhere decided that 4 apostrophes was just too much. So once we get to fourth derivative, we just start putting what derivative it is. We put it in parentheses so that it's not mistaken for an exponent. So f parentheses 4x, that means fourth derivative. Fifth derivative, like I just said, this notation's never going to change. All we have to do is keep increasing that number. But with the f notation, we would have f parentheses 5x, f parentheses 6x for sixth derivative. So let's try one of these really quick. I know this video is probably one of our longest evers, but this section is one of the most important so far. We are going to find the first, second, and third derivatives. Of f of x equals x to the fifth plus 9e to the x plus square root x. And this is our last problem of the video. It's going to take a few minutes, but this is our last one. We want to find the first, second, and third derivatives. So we have to do these one at a time. I can't jump straight to the third derivative. We have to start with the first derivative. We have to apply all of the derivative rules once. That will be our first derivative. Once we apply all of our derivative rules once, we can take that answer and apply them again, and that will be our second derivative. And then we can take that answer and apply them again, and that will be our third derivative. So if we apply all of the rules once, there's one thing we need to rewrite here, remember, square root of x, we want to rewrite that as x to the half, so we can do power rule on it. So we're going to go through and do the derivative rules on each of our three terms. The derivative for x to the fifth, the more and more you practice this, the faster these will go. The derivative for x to the fifth is 5x to the fourth. The derivative for 9 e to the x is 9e to the x. The derivative for x to the 1/2, we've done this a couple times now. Old exponent comes out, subtract 1 for the new exponent. And you're going to get 1 over 2 root x. Unsimplified, that would be 1/2 x to the negative 1/2. And we're going to want it in this form to continue on for our next derivative. But this is the simplified form of f prime of x. That's our first derivative. Now for our second derivative, we're going to apply all of our derivative rules again to the first derivative. You take your previous answer and you just apply the rules again. So f double prime, I'm going to take the derivative of these 3 pieces. And that's why I wrote this what it would look like unsimplified, because remember, we like those roots written as powers, so we can do power rule on them. So the derivative for 5x to the 4th, that's going to be 20x cubed. The derivative of 9e to the x is 9e to the x. And then the derivative for 1/2 x to the negative 1/2, it's just a power rule. We're going to bring the negative 1/2 out front, and that's going to be a negative 1/4. The new power, I'm going to write this in blue over here. This is negative 1/4 x to the negative 3/2. That's the unsimplified form. The simplified form is going to move it to the denominator with a square root and an x cubed. That is our second derivative, because we applied all of our derivative rules a second time. And we're going to do it one more time. And again, I kept the unsimplified form of that guy here because we need it to be written as x to a power to do our derivative rules. So x triple prime, that's going to be our third derivative. All we do is apply our derivative rules again to our 3 pieces. The derivative for 20x cubed is going to be 60x squared. The 3 comes down to multiply by the 20. New power is 1 smaller. The derivative for, oops, I've got a mistake here. That should be e to the x. I'm glad I saw that. The derivative for 9e to the x is 9e to the x. And then the derivative for our last term here, we've got it written in power form over here. We want to bring the old power out front. And when we do that, we're going to have negative 1/4 times negative 3/2, which is positive 3/8. The new power is 1 smaller. If you subtract 1 from that, you get negative 5/2, which means we have a square root in the bottom with a 5th power. That is our third derivative. And we could do this all day long and get 4th derivative, 5th derivative, 6th derivative, 7th derivative, as long as we want to. We could keep applying our derivative rules over and over and over and over again. And you always work off of your previous derivative to get the next one. Okay? So that is the beginning of our shortcut rules, and I promised you we would have a list here of just the rules all together at the end. So we started with the constant rule that said the derivative for a constant is 0. And then we had the linear rule that says the derivative of any linear function. Remember, derivative is tangent slope, so it's just the slope, which is always the coefficient on your x. And then we had the power rule, which says the derivative of x to any power. You're going to bring the old power out front and subtract 1 to get the new power. And then we had the constant multiple rule, or the coefficient rule, that says if you're taking the derivative of some function that has a coefficient, you really are just going to carry the coefficient over to your answer and take the derivatives of just the pieces that have x's. So that c, the c is the constant multiple. It just gets transferred to the answer. And we got 2 more. We've got the sum and difference rule. And that is for when we're taking the derivative of an expression that has multiple terms separated with addition and subtraction. And we can just take their derivatives individually and just keep the addition or subtraction in between them. So the primes there mean that we took the derivative. So this is just f prime plus or minus g prime. And then the last rule was for exponentials. The derivative for e to the x is e to the x. So there's quite a few of them that we learned here. And we're going to learn even more. The best thing you can do is lots and lots and lots of practice. Lots of practice with these.